Till now I have been talking to you about the two planetary missions of ISRO. I will now talk about the astronomy mission of ISRO to study stars, galaxies beyond our solar system. This is a unique mission because it has experiments developed by several institutions within India and abroad for this mission, and these institutions are outside of ISRO and Department of Space. So, this mission involves several scientists from many institutions, as I will indicate to you in the coming slides. The Astrosat mission is an Indian multi-wavelength space observatory. We call it a space observatory because we can actually point to specific stars or galaxies based on proposals made by any researcher within India or abroad using the satellite. So, this is the first dedicated Indian astronomy mission aimed at studying celestial sources in X-ray, optical and UV spectral bands simultaneously. This was launched on 28 September 2015 from Sriharikota into a near equatorial orbit of 650 kilometers with an inclination of about 6 degrees. Now, why near equatorial orbit is because the higher latitudes of Earth again have higher charge particle background, and so we would like to have minimum charge particle background for this satellite. And why 650 kilometer orbit is to avoid as much of the atomic oxygen which would then affect the UV telescopes. Hence, this orbit and this inclination is chosen for this mission. It has already completed 3 years of operation, and it is, as I said, being operated as a space observatory based on proposals from Indian and international scientists. It has 5 main payloads, and it also has a charge particle monitor as the 6th auxiliary payload. This is the satellite. This slide shows you on the left the satellite under preparation and the liftoff of PSLV C-30 during launch. The satellite itself just before launch looked like this at a close up, and I can show you the different payloads. This is the UV imaging telescope called the UVIT. Then we have the large area X-ray proportional counter called the LAX-PC, the soft X-ray telescope called the SXT, that is here, the UVIT is here, the LAX-PC are these 3 on the satellite. Cadmium zinc telluride imager is here behind this white board, and the scanning sky monitor is here looking towards this direction. Now, many people ask me this question, why is this golden color seen in many satellites? All these experiments have to have what is called a thermal blanket. That means it is covered with plastic like sheet, which is either mylar or made up of mylar, or it is made up of Kapton usually, and this Kapton, when it is thicker, becomes yellow in color, and it is aluminized on one side. Therefore, it looks shiny and yellow, and so these form the thermal blankets for each of these experiments, and that is why it looks yellow in color. So, the Astrosat payloads after launch, the configuration would look like this. Why I say after launch is the telescopes especially are covered with doors which are opened after launch. So, the UVIT UV imaging telescope has these two doors. It has both NUV and FUV. It operates all the way from 130 nanometers to 300 nanometers. We also have a visible channel. However, the visible channel is mainly used for correction for drift of the satellite. We have the large area X-ray proportional counter. It operates from 3 to 80 keV, and it is mainly to study the fast time variability, and it has the wide spectral coverage 3 to 80 keV by a factor of almost 25 to 30. Now, please note, here I told the units in nanometers, and here I am telling it in keV. In optical and infrared and UV, we operate these telescopes as if they are like optical telescopes, and therefore, we often refer to the wavelength in nanometers, microns or angstroms. However, when we move over to X-rays, we actually detect individual photons, and therefore, the energy of the photon is what we refer to, and that is in the units of kilo electron volts. Just for comparison, a blue photon in visible range would be having an energy of 3 electron volts, and you can see the X-rays are all in kilo electron volts. That means, we are talking of energies 1000 times or higher compared to the blue visible photon. So, this operates in 3 to 80 keV, and then we have the soft X-ray imaging telescope again here, which had a door, with the door has opened after launch, and this is operating in 0.3 to 8 keV energy range. We also have a cadmium zinc telluride imager, which extends the higher energy range to 100 keV, and it operates from 20 keV to 100 keV. And the scanning sky monitor, which is on this face of the satellite, this panel of the satellite, and it is used to detect new X-ray transients and also monitor the known X-ray sources for any variability or increase in brightness whenever it happens. So, the Astrosat mission itself, the niche area is that it does simultaneous multi-wavelength observations using a single satellite. Otherwise, you would have to coordinate between a satellite which has UV capability and another satellite which has X-ray capability. One satellite which has this multi-wavelength capability is the SWIFT satellite of NASA. It also has UV and X-rays. However, it does not have far UV observations. So, and as I have already told you, Hubble Space Telescope does have a UV capability, and it has much finer resolution compared to our UVIT, and I will come to that later. This is mainly to understand high energy processes in binary systems, specifically X-ray binaries which contain neutron stars and black holes as one of the components of the binary. We also could estimate from these sources magnetic field of neutron stars using cyclotron lines. Then with the UV imaging telescope itself, we could image star birth regions and high energy processes in extragalactic systems like active galactic nuclei. And as I told, you can detect new transient behavior from X-ray sources using the SSM. You can also study hot stars, galaxies, and can also deep field survey of specific fields in ultraviolet. The wavelength coverage in a schematic form is given here. This is the photon energy, and as you can see, the SXT, LAX-PC and CZTI have considerable overlap in their energy range, and I will come to it quickly. Why this overlap is needed is because in space we have to intercalibrate these instruments. On ground, we can calibrate these instruments with specific sources at specific energies, and often the calibration is done keeping the source at the maximum, maybe about a few meters height. So, that source is still a diverging source. So, whereas in space we are seeing sources, the celestial sources are very far away. So, actually the incoming radiation is parallel, and that you can simulate only on ground, or you have to use facilities like which was used for Chandra telescope of X-rays, several kilometers long. So, what we did, for example, was to calibrate these instruments in space after launch, and we used some time to verify the performance of each of these instruments. So, just to demonstrate to you why we need to intercalibrate, for example, this is a simulated spectrum of a blazar. Now, these three instruments, LAX-PC, SXT and CZTI, have different effective areas. The larger the area, the more counts the instrument can collect. In that respect, LAX-PC has the largest area, CZTI has the next, and SXT has the least. However, it also depends on the spectrum emitted by the source itself. As I told you, the SXT is very good at lower energies, and the CZTI is very good at higher energies. So, if the source is a what we call a soft source, that means it emits larger number of photons in the lower energy, then SXT will get a larger signal compared to CZTI. So, to intercompare these and then to make a spectrum all the way from 0.3 keV to 100 keV, we need to scale these up based on observations of standard sources with these instruments. In X-rays, we often use Crab nebula and its pulsar for calibration. Primarily, the continuum is calibrated with the Crab nebula. So, let me just briefly go through the design of Astrosat instruments, and so that you will also know the contributions from various labs around India and abroad. So, the ultraviolet imaging telescope, as I said, is FUV and NUV. It consists of two telescopes, one telescope having the NUV and the optical, the other telescope for far ultraviolet, and it consists, the telescopes itself consists of Ritchey-Chrétien telescopes, and intensified CMOS is used as the detector. The detector is developed along with Canadian Space Agency. This is the first time we have developed ultraviolet optics, which was developed in the Laboratory of Electro-Optic Systems of ISRO. So, this is a collaboration of Indian Institute of Astrophysics, IIA, in collaboration with Canadian Space Agency, and in all these payloads several of the ISRO laboratories are involved, and so I am not putting ISRO in every slide. And let me tell you that the UVIT has the best resolution of 1.5 arc second with a large field of view. Please combine this with a large field of view, because HST, as I told you, has the best UV resolution. However, HST has a small field of view, whereas we can with the UVIT image the galaxy in one snapshot with a resolution of 1.5 arc seconds. The large area X-ray proportional counter is the LAX-PC. this consists of actually proportional counters, as you may all have studied in nuclear physics. It is a practical application of proportional counters, and it has gas filled at about 2 atmospheres, and it is sealed with a very thin window of 50 micron, and it has about 5 times the effective area of at 25 keV and above compared to the Rossi X-ray timing explorer, which was the previous similar experiment flown by NASA. So, this is led by Tata Institute Fundamental Research along with some collaboration with Raman Research Institute, and it has, as I told you, all the three together had a 8000 square centimeter area, and it can cover the energy range of 3 to 8 keV energy range. Soft X-ray telescope, it has an energy range of 0.3 keV to 8 keV. Again, first time we have developed Indian indigenous X-ray optics, which is aluminum foils coated with gold, and the detector itself is from University of Leicester, UK, and the assembly etc. is done at Tata Institute of Fundamental Research. The optics is also done by Tata Institute of Fundamental Research in Mumbai. The UVIT and SXT are imaging instruments with optics. The LAC species has what is called the collimator, which limits the field of view to 1 degree by 1 degree. It is not an imaging instrument. Similarly, cadmium zinc telluride, this is a coarse imager, it is called CZTI. It has a collimator, but in addition to a collimator, it also has a coded mask with which we can image to few arc minutes level. So, this is a solid state version, that is, it uses detectors called cadmium zinc telluride detectors. These are solid state detectors, unlike the gas filled detectors of LAC species. It can give slightly better resolution than LAC species. It also can extend the energy range to 100 keV, and beyond 100 keV this collimator actually becomes transparent. So, the detector is here. So, till 100 keV you can only see photons coming from above entering through the collimator. However, beyond 100 keV it can also enter from the sides and so on. So, this aspect is actually used to detect gamma ray bursts from this using this instrument. The scanning sky monitor, this is, as I told you, consists of again gas filled proportional counters, but this time it is position sensitive gas filled proportional counter. So, even though the SSM has a large field of view of 90 degree by 24 degree, it can actually find the position to few arc minutes in this large field of view, because again it has a coded mask above the gas filled proportional counter. It is developed by ISRO Satellite Center. There is a group called Space Astronomy group at our center, then known as ISRO Satellite Center ISAC. So, now let me give you the glimpse of results from Astrosat. I told you UVIT has a very good resolution. This is demonstrated in this slide. A similar telescope called the GALEX, which was from NASA, was flown, and it could image galaxies in single snapshots with an with a spatial resolution or angular resolution of 6 arc seconds, whereas we can do it with 1.5 arc seconds, and you can see the features which are resolved compared to this image in this image. And as I told, this we can now resolve as a separate galaxy. It is not a combination of stars, and the spiral arms are also clearly visible. Here this is a slide to show you the effect of for example integration time. This is an image in NUV and this is the image in far UV for the same time. Now, most of the spectra of celestial sources, as we go higher and higher in energy, the number of photons emitted by the source decreases usually, and therefore, for the same integration time, the source will appear much brighter in optical, then less brighter in NUV and least bright in far UV. So, for the same time, as you can see, we see less photons in FUV, but if you give a long enough integration, even in FUV you can resolve the sources. That was a galaxy with spiral, it was a spiral galaxy with the spiral arms shown very clearly. This is an image of globular cluster, and you can see that we are now able to see, compared to galaxy, resolve much more sources closer to the center of the globular cluster. Now, globular clusters have tens of thousands of stars within a small region of few arc minute of few arc minutes, and it is essential to identify these stars and study each of them separately, and so it is necessary to resolve these sources, and you can see that we can resolve these compared to galaxies. So, let me give a brief description of the one of the initial results of the UV imaging telescope. As a calibration target, the open cluster NGC 188 was observed. You can see the image of this target, and you can see that the NUV has many more stars compared to the FUV. Earlier results using the UIT observations actually identified two stars which were probably binaries, and these were very faint in optical and therefore could not be actually understood whether they are really binaries or some other type of source. So, UVIT observed these sources. So, one of these sources, the one marked in red, and this is called WOCS 5885. UVIT, as I told you, covers the energy range from 130 nanometers to 300 nanometers. However, there are several filters in these bands, and we can take images of these objects in each of these bands, and having taken images, each of the stars can be measured, the flux from each of these stars can be measured in each of these filters. So, if I plot with respect to the wavelength, if I plot the flux which from this WOCS 5885 star, I can get several points on the flux wavelength scale. So, the light green points are the points obtained from UVIT. The red points are from the earlier observations of galaxies. Some of these points in the optical and infrared are based on ground based observations. Based on all these points, it was found that it could not fit with a single black body spectrum. This could be fit only with two spectra together, and those two spectra correspond to a cooler star, which is a blue straggler star with a temperature of about 6000 Kelvin, and a hotter star which is about 17,000 Kelvin. So, as I told you right in the beginning, we receive information, we have to analyze it, and then we have to interpret it. The interpretation of this observation of fitting of two temperatures and therefore two stars is that this source could be a rare binary of a blue straggler and a post AGB star which is hot, and this, if it is indeed true, then it could be the first of its kind to be identified in an open cluster. We now come to the soft X-ray telescope. I told you this is also an imaging telescope. However, the imaging is of the order of few arc minutes. And when we calibrate this kind of telescope, we often use a supernova remnant as our calibration source. As I told you, the soft X-ray telescope has good spectral resolution. That means it can detect spectral lines because it uses a CCD as the focal plane instrument, and inherently, as I told you, we detect each photon. So, we can actually detect the energy of the photon as we detect in the SXT. So, we get an image which is formed due to contours of equal flux, and we also get a spectra which is a function of energy, and you can see the individual lines from this supernova remnant. You may all be aware that supernova remnants are the regions where high mass elements are actually what we term in layman terms cooked, or they are actually formed in nuclear processes in supernova explosions. So, all the higher elements higher than hydrogen, helium, carbon, etc., are most likely formed in supernova remnants. How do we really identify these lines are indeed falling at the right place? We actually compared this data also with Swift data, and the black and the red curves are from Swift for two different settings of the data set, and blue and the green are those for SXT, and since the lines match very well, we know that this is calibrated well for these lines. And then I told you that one of our main aims is to study X-ray binaries for black holes and neutron stars. When massive stars greater than actually even 8 solar masses can when they exhaust all their nuclear fuel in the center, they might collapse into black holes. If the stars are about 4 to 8 times the mass of the sun, they might collapse into neutron stars. Now, how do we study these neutron stars and black holes? Neutron stars actually can be studied in radio in the form of radio pulsars. However, black holes, if they are isolated, it is very difficult to detect them, leave alone study them. So, one way of studying these black holes is when they are part of a binary, that is, one star is a black hole and the other star is a regular star. It might be a blue giant star or it could be a low mass star. Now, as you would have heard in physics classes, there are these Lagrangian points which are associated with the binary system. So, this black hole and the star are actually going around each other in the binary system around the center of mass. But however, when the companion star actually evolves and when matter from that companion star crosses the first Lagrangian point, and it is called, actually in astronomy terms, the star evolves beyond its Roche lobe, then it can transfer matter to the companion star. In this case, the companion star being a black hole or a neutron star, it has a very high gravity. Black holes are suspected to be point objects, whereas neutron stars have a size of few tens of kilometers, maybe around 15 kilometers radius, and they have a mass of 2 to 3 solar mass. So, just imagine 2 to 3 suns put compacted into a region of 15 kilometers radius, which is the typical size of a city. So, this leads to what is called compactness of the object, and therefore, the gravity on neutron star is very, very high, of the order of 10 to the power 14 to 10 to the power 15 centimeter per second squared. So, this is of the order of 10 to the power 11 times the acceleration due to gravity you experience on Earth, and that is why mass, anything massive on neutron star will be 10 to the power 11 times more massive compared to what it is on ground. So, due to this, the gravity is very high. So, any matter which comes from the companion star, either in the form of stellar wind or in the form of matter due to the star expanding beyond its Roche lobe and matter coming to the Lagrangian point, will be sucked in by this gravity of this compact object. However, that matter can't directly fall onto the compact object because it has an angular momentum corresponding to the companion star. Therefore, while it falls on to the compact object, it will actually form a disk around it, and then only the matter will fall on to the compact object like a neutron star, or it will fall into the event horizon of a non-rotating black hole. So, what we can then observe this matter while it goes around as the accretion disk, and as the matter falls into the inner regions surrounding the black hole till the matter disappears and we cannot observe it any longer. So, this accretion disk is a very flattened disk, and it has friction between layers of the disk. So, the accretion disk becomes hotter and hotter as you go to the inner layers. So, while the outer layers are very observable in optical regions, the inner layers are observable in UV, and the innermost layers are best observed in X-rays. That is why the region around neutron stars and black holes in these X-ray binaries are best observed in X-ray part of the electromagnetic spectrum. So, we do this with timing and with a best time resolution of 20 microseconds. Now, can one aspect of this, I told you it is very difficult to detect black holes, and one way is by studying these black holes in binaries. Now, there is one further difficulty, and that is these black hole binaries do not emit in X-rays all the time. The accretion disk itself is not bright all the time, it is very, very faint. We still do not know why, but so most of the black hole sources most of the time are below background level in the sky. So, often when you see that region of where the source existed earlier, you will see it below background level. It is only when they go into outburst that you can see it as a black hole source. So, that is one reason. So, often black hole sources of binaries are termed as transient sources. There are, for example, very few persistent black hole X-ray binaries. Cygnus X1 is one which, however, exhibits variation in spectral states. So, in order to find whether these black hole binaries are in outbursts, we need to actually scan the sky and detect which source is going into outburst. It might be a known source which had gone into outburst earlier. It could also be a new source which had not been detected so far as a black hole binary, which goes into an outburst now. So, that is the reason the scanning sky monitor is having 3 detectors with different fields of view, and it is mounted on a rotating platform to cover as much of the sky quickly, so that when this transient occurs, we can capture it, and then once the SSM indicates that there is this transient in a new source or in the existing source, the Astrosat instruments can point to that source and actually observe the source. So, now I will tell you about a result of a source which is called GRS 1915 plus 105. This is a black hole X-ray binary, now termed as a micro quasar. The reason being it also emits superluminal jets like active galactic nuclei, or what is termed as quasars. So, this is called as micro quasar because it is has properties similar to quasars. However, it has a black hole which has mass of the order of 20 solar mass, unlike quasars which are having supermassive black holes at their center. So, now we have this matter falling into the, how do we know that this is indeed a black hole? So, this is data from 1996 from the Indian X-ray astronomy experiment. We and the RXTE experiment satellite detected this matter falling onto the black hole. Usually these kind of transients will be fast rise and slow decay. However, this is unique. It has a slow rise and a fast decay, which we interpreted as matter falling onto the event horizon of the black hole. And you can see that this light curve, this is time versus intensity in the form of counts. This light curve varies drastically within few days. So, this now RXT has found is due to change in various spectral states which this unique source demonstrates in time. So, you can see there is change in light curve, there is also change in spectral state. So, this source is a very important source, one because it became available as a transient only from 1992, but it is one of the unique sources which has remained bright even now. This source was also observed by SSM because it is a very bright source, and even with the low effective area of SSM we could detect it, and this light curve, as you see, is very similar to the RXTE light curve, which is shown here below. RXTE has effective area of thousands of square centimeter, whereas we have just about 60 square centimeter in area, but we can see that the light curve is very demonstrative of the beta class of variability in this source. So, as I said, it shows many spectral classes. So, it's the variability is also structured, and there are different classes. So, alpha, beta, gamma, etc. There are some 13 classes of variability in this source. So, this was, as I said, was observed by SSM. Then in this source, we also detect what is called quasi-periodic oscillations. Now, this source has a quasi-periodic oscillation at 2.55 hertz. However, in the energy band of 20 to 80 keV, it was first detected with lac species. As I told you, in the higher energy range, lac species is much more sensitive than the earlier RXTE, and therefore, we could detect this QPO in lac species in this energy range. Why is it so important? Quasi-periodic oscillations, we do not know the exact mechanisms of quasi-periodic oscillations, but it is expected that these are oscillations occurring in the accretion disk, and higher the energy range, closer it is to the black hole. So, there is also this fact that this quasi-periodic oscillations change with time, and so you can actually when you observe it with time and with energy, you can actually map whether the where the quasi-periodic oscillations originate and probably how it is varying with time and how it is connected with other factors like emission of jets, etc. So, these kind of studies are going on regarding quasi-periodic oscillations. Finally, I come to a result from cadmium zinc telluride. I told you that there are this instrument beyond 100 keV can detect gamma ray bursts. Gamma ray bursts are again transients occurring in the sky, some of the highest energy transients, and these are can again occur anywhere in the sky and can also occur at any time. So, again you have to have a wide field instrument to actually detect these sources and actually triangulate and find their positions where it has occurred for them to be studied in other wavelengths. SWIFT is one such telescope launched by NASA primarily to actually detect gamma ray bursts and to also study them in X-ray and UV ranges. So, CZTI now is one of the satellites which can also contribute to this detection of gamma ray bursts, and as I told you that CZTI now has a unique capability of finding polarization in these gamma ray bursts. So, we can actually detect polarization of emission from these gamma ray bursts, which then will limit the models of these gamma ray bursts. We have also studied polarization from crab itself, and we have found this polarization as a function of spin cycle of the crab pulsar. Now, polarization from crab itself was detected in the early 70s, but as a function of spin cycle we are the first to detect this, and we find that in fact the polarization fraction may not actually be in phase with the spin cycle. So, this is one of the important findings from Astrosat. CZTI can also contribute to gravitational wave detection in the form that it can possibly detect electromagnetic radiation when two neutron stars collide. Till now, we have not had any direct detection. However, in the case of one gravitational wave detection, we have found that something which was a burst of intensity in Atlas was conjectured to be associated with the gravitational wave detection, has now been identified that it is indeed with a gamma ray burst rather than a gravitational wave detection. So, whereas in another, even though CZTI did not detect it, we could say we could not detect it because our satellite was under earth occult, and therefore, the localization should take this into account to actually find the localization of the gravitational wave. So, in future we hope that we would actually directly detect electromagnetic radiation from gravitational waves. And SSM has detected Aquila X1 in one of its outbursts. Aquila X1 is a source which repeatedly goes into outburst. So, we could actually detect it in outburst. It is a neutron star binary. Just let me conclude now. As I told you, there are several institutions involved in the success of Astrosat. So, along with ISRO, Tata Institute of Fundamental Research, Mumbai, Indian Institute of Astrophysics, Bangalore, Inter-University Center for Astronomy and Astrophysics, Ayuka, Pune, Raman Research Institute, RRI, Bangalore. And then I told you we have two international institutions, Canadian Space Agency, Canada, and Leicester University, UK. And we also have the participation of, I said expected, we do have now, of many universities and other research centers, because as I said, many of them are proposing to Astrosat to observe specific targets, and the flow of observation plan is the proposers actually, there is an Astrosat proposal system, APPS. Proposers, this is a web based system which is hosted in the ISRO Space Science Data Center. So, we actually give calls during January to February. Usually the call is initiated in January, proposals can be submitted till February, March, the end date is given. So, proposers can submit proposals. This is then the Astrosat time allocation committee along with Astrosat technical committee approves some of these proposals, and these go into mission operations, and these are the requirements are checked and operations are conducted, actual observations are conducted like an observatory. The data is received and data products are generated, and this data is disseminated at the Space Science Data Center, and it goes back to the proposers. It first goes to the payload operation centers, gets validated, then goes to the proposers, and after the lock-in period of 1 year, it is made open to anybody in the world to use this data. So, I now end this talk with a picture of the special issue which we brought out on Astrosat. We also bring out Astrosat picture of the month along with the outreach team of Astronomical Society of India and the Astrosat Science Support Cell at Ayuka and Indian Space Science Data Center. So, in case I would like you, I am not giving the web address, please go to the Indian Space Science Data Center web, and find out the availability of data from all these observations from these missions. Thank you.